All right. Welcome back. Let's get started here. All right. Has everyone finished the active homework? Or any issues still? Oh, okay. If you show it to me, maybe after lab or something, we can get that straight out. But it's not impossible.
It took me a while to figure out, but I did figure it out.
Okay. All right. I think the hardest part is just doing it the first time. Yeah, but it's like that sometimes, especially with these with the homework systems. Yeah, it's harder to like just draw it.
There's also one that's like a super long like triple bond. I will have to ask that after that because I somehow got it. I still don't know how to do it.
Okay, we can talk about it. All right. So, are there still issues with active, or are we able to complete the homework? Still some issues? All right. If there's still issues, I'll extend the homework through Monday. Okay, but think about completing the homework soon because I'm going to post a second one. All right. And the second one will let's see here. Focus on acid bases, resonance, and yeah, what else? What else? Oh yeah, formal charges again. Okay, so I'll post that one probably tonight when I get the time. But let's pick up where we left off. All right, let's settle down here. Okay, so we're going to finish talking about resonance, and then we will jump into acid and bases. Okay, all the definitions. Do a review of acid and bases, and then the quiz will be towards the end. Okay, so I hope we're all ready. If not, I hope we're ready by the end of today. Okay, so last time we talked about resonance structures. Okay, rule number 2 was the structure of the most octets for atoms, right? The most octets you have, it typically is the best resonance structure for the molecule. Okay, so for example, you have this molecule. Well, okay, you see there's a positive charge on carbon. Well, carbon, although carbon, according to electronegativity, right, carbon's okay having a positive charge, but usually when carbon has a positive charge, there's no octet. So that's bad. Okay? So it's better if we have it fully with octets. So something like that. Like that. Okay? So this one on the right has the most octets. Everything has an octet. Carbon and oxygen. So that's the major contributor. So we call that the major contributor. Or, the most important form. I almost forgot something. All right, so before I forget, can we sign in for today? All right, and I also have lecture attendance today in lab too. Okay. Now, let's talk about, all right, so that's rule number 2. Let's go to rule number 3. Okay, so what about charges? Do you remember how charges play a role in the resonance structures? Charges, right, should be on atoms with, the appropriate or the correct electronegativity. So things with higher electronegativity, you should put the negative charge on those atoms, right? Because it likes the negative charge. And then things that are less electronegative, they prefer positive charge, okay? So I'll give you an example. Appropriate electronegativity. So I might abbreviate electronegativity from now on as EN, sorry. Just because it's a mouthful to say and just write out, okay? So here's an example. We have this negative charge on carbon. All right, and this is an aldehyde. We draw the resin structure like this. Okay, so I moved the double bond, the lone pair, into a double bond. And now I get the negative charge right here. Okay? So here, the negative charge prefers to be on oxygen because that's one of the more electronegative elements. So it's happier with the negative charge. Because of its position on the periodic table. Okay, so this would be our major contributor. All right, and we'll get more practice drawing these resin structures today in lab. All right.
I have a question.
Yes.
When you say major contributor, are you saying like the whole molecule itself, or is there an element within that?
Oh no! So this structure is the major resin structure for the whole compound. Yeah. So remember these resin structures. What's actually the real picture is the hybrid. But when we say major contributor, it's telling us that this structure makes up a majority of the actual Lewis structure. Okay, so it's not 50-50 now, like we said with the previous example last time with the benzene ring. Those two structures are equal weight, actually, equal importance. Yes, good. So this whole structure is the major one. That's a fair way to put it. Okay, so any questions about the charges? We're okay with charge. Negative charge, put on more electronegative elements. Positive charge on hydrogen or it can be on hydrogen, on carbon primarily. Or if you have something like oxygen and nitrogen, the positive charge will prefer to be on nitrogen because that's less electronegative than oxygen. Okay? All right. Any questions? No? All right. So number 4. The fourth guideline. When you have a structure with least charge separation. So you don't want charge separation. So we have opposite charges. So opposite charges, you don't want to put them far away because that's unstable, right? They prefer to be close. And if you have negative charges, you don't want them to be next to each other because that's unstable. They'll repel. So think about how charges attract, like opposites attract, like repel. And I'll tell you something about the structure, if it's a good one or if it's not a very good one. Okay, so structure with least charge separation. But the best thing to have is no charge at all, if possible. Okay. Got H. So this is formic acid. In some insects, like the bombardier beetle, it uses this formic acid as a defense mechanism. All right, and it's quite potent because it's a very strong acid. It will good deterrent for predators. Okay, so All right, so say we have a negative charge there. We're just moving the lone pairs here like we did before. And we see here that now one structure has no charges. One structure has separated the charges across the molecule. So that's not very stable, okay? So this one is more important. So here, this one would be the major structure. All right, so so you can say major structure. When I say major contributor, maybe that didn't make a lot of sense. So I'll just say major structure now, okay? So this is the major Lewis structure for this molecule, but the second structure still plays a role in the actual structure. Remember, the hybrid, okay? I know that concept may sound a little strange, but we're gonna have to think about that the real structure is like an average of all the structures, okay? Somewhere in the middle, right? Okay. So, so that's it for like the guidelines for resonance. Now I'm going to talk about something you might have saw in the homework where it said, what is the hybridization? And you might have guessed what you thought it was, and it turned out it was incorrect because we didn't consider the resonance structures. I'm going to go over that briefly. Are there any questions, though, before I go over that? No? All right. So let's go now to an example. So I'm going to draw a line here. Let's do an example here. All right. So in my example, I'm going to talk about hybridization in resonance structures. So when you're studying hybridization, you always have to consider a few things first. If there's no double bonds, there's probably no resonance structures, so you just assign hybridization. But if there is an atom you're interested in, and there is the possibility to write a resonance structure, you have to write that first and compare the two. All right? So I'll explain what I mean. So what I want you to do here is determine the hybridization and molecular shape of nitrogen in aniline. Okay, and I want you to explain briefly. All right, aniline, I will have to draw aniline for you. So aniline is this compound. So it's the benzene ring with a amine group attached off it. All right, so this is aniline. Okay, so that's aniline. All right, so if I were to give you this, if I were to ask you what's the hybridization around nitrogen, what would you say? Yeah, around the nitrogen atom. So what's this hybridization? What do you guys, well, based on what you learned, right, what would you say? sp3. But no, that's completely wrong. It's not sp3. This molecule is actually pretty flat. And what kind of hybridization we associated with flat? Or planar. So this molecule is actually planar. So it doesn't really make sense why it's planar, and we can't see that unless we draw the resonance structure. Okay, so I'm just going to show you a few arrows. So I would take this arrow, and I'm going to form a double bond here. Okay, so now when I form a double bond there, I can't just do that. I have to do what to the double bond now? Yeah, I'll have to, okay, move it, right? Move it where? So don't worry about moving this arrow. Don't worry about moving the double bond far. Just break the double bond and put it on the adjacent carbon atom right here. Okay? That's just because we don't have to draw all the possible resonance structures. Let's just draw one. Okay, this is just one of them. All right. So I didn't do anything here, right? So we know we just put the lone pair here, and or we broke the bond and put a lone pair there. So once we do that, so remember, carbon with a lone pair, always negative charge, okay? For what we've seen before, so far, okay? Now this nitrogen is now going to have what kind of charge? No, sorry, charge. Formal charge? Yeah, positive. Now, if we compare this nitrogen now, we can write this out. Nitrogen now has a double bond here, right? And two hydrogens. So what's the hybridization on the nitrogen now? sp2. All right, that's actually the hybridization on nitrogen. Now, in reality, it's not that straightforward, but we're just going to accept that, okay? It is pretty much sp2 hybridized. All right, so the reason for this is when you have resonance structures, to assign hybridization, you can't just look at one structure. You have to consider both of them. So you're always looking at the structure that has the most bonds around the atom in question. So which resonance structure has the most bonds around nitrogen? Is the one on the left or the one on the right? Yeah, okay. So I'm just going to abbreviate my explanation here, okay? So you want to look at the resonance structure with the most bonds around nitrogen. Okay? So we understand that in the second structure, right? It has 3 electron groups around it, okay? And that's the group where there's actually more bonds around nitrogen, right? Because in the left group, left structure right there, nitrogen only has 3 bonds on the left structure, right? So that's why we don't consider that structure. We have to consider number 2. Okay? So when I learned OChem, I actually didn't learn this until I went to Davis. So that's how we assign hybridization. Okay, I used to assign everything. If everything had 4 groups around it, sp3. But it changes when something can participate in resonance. Okay? All right. So let me just write here, nitrogen has 3 electron groups around it. Okay, so let's just name them right now. So we have a bond to H, a bond to another H, and then a double bond to the benzene ring C6H5. Okay, so this corresponds. So this will give sp2 hybridization, hybrid, and a planar shape. Okay? All right. So Why does it have to be planar to do resonance? So how do double bonds, kind of interact with each other? Through which orbital? The p orbitals, right? So a good way to realize how these electrons are moving is if you just draw a skeleton here. Okay, so let's just draw the skeleton of the NH2 group. All right, and let's draw the ring structure here. Okay, so I'm going to put these double bonds like this. Okay, this is where that carbon was at. So if I draw the p orbitals, that negative charge is in that p orbital, right? But since there's double bonds around the whole molecule, you actually have p orbitals surrounding the whole molecule. So something like this, like that. Looks like a bunch of satellites kind of in parallel, or like power towers, electrical towers here. So the reason why electrons can move like this is because all the p orbitals are aligned, and that's how we can remove the electrons. Okay, and then since NH2 is hybridized in the sp2 fashion, there's actually a p orbital here that's holding that double bond together. Okay, so that's how we should think of resonance. There's a series of p orbitals. So you don't have to draw that. You're not responsible for, reproducing that, but that's just kind of illustrate conceptually what the electrons, how they communicate / move throughout the structure. Okay? All right, are any questions about that? Catherine.
But doesn't this break rule 3 about the electronegativity? Because nitrogen is more electronegative than carbon. So we really want the nitrogen to be negative.
Yeah, it does, but this is still a valid resonance structure, so we still have to consider it. It doesn't break like any cardinal. The first rule, which is everything still has an octet, right? So that's still so the importance of these guidelines, they go from like most important, number 1, and then least important, 3 and 4, when you have to kind of break a tie between them. Yeah, but good question. Any other questions about resonance structures? So resonance structures, even though one doesn't look good, that just means you still have to consider it in part of when you're trying to understand reactivity. This whole thing about reactivity, the fact that this structure can't exist kind of tells you, oh, it's less stable, but that means it's more reactive. So that's how it explains chemical reactivity, as we'll see later down the line. Okay, any questions about that? Nope? All right. So when you're assigning hybridization, always look at the structure with the most bonds. Let me just highlight that, most bonds around the structure, okay? That will be your key word here. And the practice we'll do today in class, okay? All right. So the next thing we'll do is talking about isomers, okay? Chemical formulas and structural, constitutional isomers. All right. So do we all remember what an isomer is? So C2. All right. If I were to draw an isomer of this, of a structure, right? Isomers are compounds with the same formula, but they have different what? Yeah, different, structures based on the connectivity. Yeah, and pretty much the visual way to think about it is different shape overall, okay? Like one might look like a line, one might look like a blob or a kind of circular or branched. Okay, so let's use this structure, this formula. Draw all possible Lewis structures. All right. So the best way to start here is kind of go in a line first and then try to flip some atoms around in the new structure, okay? So let's say we have CH3, CH2, okay. How can I complete the structure? I already got all the carbons. I got 5 of the hydrogens, missing an OH. So right here, right? All right. What's another way we can draw a similar structure with the correct formula, but the order of the atoms here are not exactly the same? Yeah. So either oxygen in the end or oxygen in the middle, because it can form 2 bonds, right? So why not? So we can also draw it like this. So this is methyl ether. Once thought of as a replacement for ethanol and gasoline, actually. Okay, so those are the 2 isomers you can draw for this. You can't draw any circles. So when we draw structures that have like a circle in it, we call them rings. So they're not actually called circles. They're called cyclic. They're connected in a cycle. But we don't actually call them circular. So cyclic alkanes or cyclic alkanes or cycloalkanes, those are when you have structures that has a closed loop. Okay? So what are isomers? Let's just recall what an isomer is. You might have to do this on the first exam. Same chemical formula. But different Lewis structure. And by definition, if you have the same, if you have different Lewis structures, that means your conductivity must be different, right? Because if it were the same Lewis structure, it would just be the same compound. Okay, so these 2 are isomers. All right, let's do an example of this. So here's my example. Why don't we draw all the isomers of this? All right. Draw all isomers. All right. So there's not that many. Okay. I want to make you draw like 20. Okay. So this is small enough where there's a few, okay? So the easiest thing to do is what? Draw what first? What kind of shape? Zigzag. Let's do the zigzag, okay? Boom. Up, down, right? Like that. Kind of how like when you had to draw the Lewis structures on the homework, you could draw lines easily because everything was like on hexagon paper. Okay, so how can I draw a different one? Flip it.
Can you start from the top?
Okay, so. Maybe now. All right. So let's take one of the ends, right, and place it maybe towards one of the central CH2s. Okay. So let's do something like this. All right. Oh, did I get that wrong? Okay. All right. Bam. Would this work?
Yep.
Yeah. Okay. And then, is there any other way we could draw another one? I'll give you maybe a minute to think about it. Okay. Well, is this an isomer, or are we not having a discussion here? Is it an isomer? It's an isomer, right?
Yes.
Yes.
I'm asking, like, so if I started from the top, doom, is it like also an isomer? But she said, no, it's the same thing. So I was like,
Oh,
you know
okay.
what I mean? Like the left drawing.
If you
If you flip it.
Oh, flip it over? No. So that's like a. So you just flipped the over and got the same molecule. So that's technically not any different. Yeah. So even if you rotate it a bit, it's still the same molecule. Okay. So let me just first. All right. So there's only actually two of them, and we drew all two of them already. Okay? So, but usually, as you get more carbon atoms, there's usually exponential more number of isomers. So it gets fairly complicated when you have towards 10 carbon atoms and many hydrogens, okay? But are there any questions on isomers? Do we all agree that they're different and that they have the same formula? Yes? All right. Okay, are there any questions on isomers though? So these are called structural isomers. And why is it structural? The Lewis structure is different, right? There's other types of isomers that we'll learn, especially stereoisomers. They look the exact same, but in 3D space, they are quite different, okay? So they will have the same connectivity. So you can have the same connectivity and still be considered different isomers, okay? Okay, and that becomes important in drug interactions in biology. So stereochemistry is pretty important. Yeah, maybe we could demonstrate that. When we talk about it, it'll be interesting. Okay, so all right, now we're going to spend some time talking about acids and bases. All right, so acids and bases is an important section. This is mainly review. But it's important because in chemical reactions, you have to consider acid-base properties. You have to consider like, oh, I know this step of a reaction, I'm going to do an acid-base reaction. You have to be able to not just memorize that, but be able to say, okay, I know this is an acid-base reaction. When I ask about synthesis, you're going to be like, okay, I need to add a proton. I need to use an acid-base reaction. So you have to have these concepts down before you even try to apply them in reactions. Or the goal of organic really is towards a synthetic or synthesis goal, making something new from scratch. And it could be anything, like pharmaceutical, OLED, so organic compounds are commonly in your phones as OLED screens. Okay, so they're everywhere. All right, but anyway, acids and bases. All right. All right. So acids and bases. All right. So most of the acids and bases we've talked about, or you've probably seen, they're mostly inorganic. But the ones we'll focus on, they're purely organic. So they're all covalent compounds. And they all have polar covalent bonds. Okay? All right. So let's go over a few definitions. So I'm going to breeze over Arrhenius because we no longer care about the Arrhenius definition very much. In Gen Chem, we covered it because that's how you measure pH based on the concentration of this ion, or POH, this ion, right? All right, so let's go over some definitions here. All right. So Arrhenius. All right. Does anyone remember what an Arrhenius acid is? So if I ask you what Arrhenius acid is, you'll probably say an acid that increases the concentration of what ion? Hydrogen ion or hydronium, right? Okay. So dissolves in water. And increases. So you can write H plus or H3O plus. I will use these two interchangeably, okay? So dissolves in water and this concentration increases. So it drives up the pH, okay? What about a base? What would the Arrhenius base do?
Increases the OH.
Yeah, drop the base, increases the OH concentration. The pH goes up, right? All right, so we saw that a lot, especially in Gen Chem, right? When we did a lot of titrations, especially here at Woodland, okay? Both 1A and 1B. All right, but that definition was like the very early definition when they were studying this. Arrhenius was studying this when he was alive, okay? But next came a better model, and it applies to a lot more compounds. So acids and bases, that's a property for many compounds. So you can actually make a compound that you wouldn't consider an acid and base behave like one, okay? And if you could somehow do that, it changes the whole game here. All right, so now let's talk about all these different colors. Bronsted-Lowry. All right. So in the term of acid in the Bronsted-Lowry or B/L definition, what is an acid? There's a specific term. So in this definition, we use the term proton. Do you remember what role an acid does? Yeah, donates a hydrogen to water, right? Or the base. Okay. So remember H plus. We can also say H plus is also just a proton because it has no electrons, H plus, right? So it only has its proton. Hydrogen has no neutrons, okay? So proton donor. I never heard it be called anything else. So donor, meaning it just gives up its proton. Acid gives up its proton to water, usually water, if that's the base, because it's in solution. What about base? What's that? Yeah, proton acceptor or accepts the proton, okay? So that's the most common definition we see. All right. So I'll give you an example of what this looks like. Okay. So NH3. So what's NH3? Usually a base, or is it usually an acid? When you react it with this. All right. Which one here is my acid? Which one here is my base? All right. Imagine these are both in solution.
The NH3 is the
Good.
HCl is acid.
Yes. So we still have to remember our strong acids, okay? I'll tell you which ones you should know. Most common ones are HCl and sulfuric acid, H2SO4. So I'll write those a lot. So every time I write them, I'll say this is a strong acid, okay? So just remember those. There's other strong acids we may see, but usually these are the most common, okay? So, and then the ammonia is the most common base you saw in inorganic, Gen Chem. In organic, the most common weak bases are ammonia and the organic relative amines, okay? So those are common bases in organic chemistry. All right, so before we used to see reactions, we just write the products, right? NH4, because that's a base, and then Cl minus becomes the conjugate base, okay? So one way to, so I usually show these arrows when I teach Gen Chem because it gets you familiar with OChem a bit. So remember, these arrows will join here, grab a hydrogen, and eject chlorine. So you now have NH4 plus and Cl minus. So this is your ammonium salt. Okay. So remember, any reaction with a strong acid, strong base, with the corresponding acid, other base, you'll generate a salt of some kind, an ionic compound. So we went from two covalent compounds. Now we generated a ionic compound. So that's how those are formed. All right. Are any questions about acid base, the arrows? You okay? All right. So now let's talk about how do we determine the relative strength of acids and bases. All right. So here's our generic reaction for an acid-base reaction. Sorry, that's low words. For acid dissolving in water, how does it ionize? So you have your generic acid, HA, and then in solution, it will dissociate or ionize partially to H plus and A minus. So we know H plus is the acid form, right? What's A minus? So here's my acid. When it separates into A minus, what do we call that? Do you want to remember? Yes, the conjugate base, okay? All right. So here's the trend here. The stronger the acid, what about the strength of the base? Is it strong or is it weak? Weaker, right? You can't have a strong acid and a strong base like exist in the same molecule because that's just counterintuitive. It will not be stable. So what we say here is the stronger the acid, okay, your conjugate base is going to be weak. So the stronger you are, the much weaker your conjugate base. Okay. And then on the contrary, we have a base reaction. Okay. Say you have a base B with a lone pair. It's going to react in water. Okay. Oh, sorry. Let me, all right, guys. Well, it's all right. If you don't, let's put H plus over here. I don't want you guys to erase it. Here you go. So base reacting with H plus, right? It will form HB. Okay. And now B will now have the positive charge. Okay. So this is our base. What's this called on the right? HB, what's that called? conjugate acid. Good. The same thing applies here. The stronger the base, the weaker the acid. Okay, so it's just the opposite now. All right. So a common question they teach you is you should be able to explain. Here's an example. Let's do the exercise here. All right. Predict the direction of the equilibrium in the following reaction. Okay. So we have NaCl plus HF. Okay. NaF plus HCl. All right. So let's predict which direction this reaction will go. Is it to the right or is it to the left? So acid-base reactions will always proceed in the direction where both the weak conjugate base and the weak acid is located. Okay. So we already talked about HCl. What kind of acid is this? Strong or weak?
Strong.
Yes. So this is a strong acid, right? Okay. Now, HF, is that a weak acid or a strong acid? Weak. Compared to what you might heard of HF is still plenty corrosive. Okay. But in terms of its ability to donate H+, it's a weak acid. Okay, so this is the weaker acid. All right. So if HCl is the stronger acid, we see in sodium chloride, there's chloride there. So chloride, what can you tell me about the base strength there? Do you think it's a weak base or a strong base? Weak, because it's from HCl, a strong acid, right? Strong acid will be paired up with a weak conjugate base. So here we can say this one right here, weak, or say weaker conjugate base. All right. And how about fluoride? Well, we have a weak acid in HF. So compared to HCl, what can we say about fluoride? Stronger conjugate base or weaker conjugate base? Stronger, because HF was weak, right? So that means F- must be a strong conjugate base. So here, fluorine, I'll point to fluorine here. Stronger conjugate base. And what I mean by stronger, compared to fluoride. Sorry, not fluoride, chlorine, okay? All right. So this combination right here is more stable. All right? More stable combo or combination. All right? So the reason why chlorine is so stable or weak, let's look at chlorine. So Cl- here is larger than F-. Okay? So the larger it is, the more we say more polarizable it is. More polarizable. All right? That's a scientific term to tell you that the atom itself is more squishy, meaning it can be deformed much easier and it can stabilize electrons more easily. So electrons are not as reactive to act as a base. Okay? So I like to say it's more squishy here. All right. And what this means is that the electrons in chlorine are spread over a wider area. All right. So this is why that's the weaker base. It doesn't want to act the base because its electrons are happy. It doesn't want to go anywhere. It's pretty comfortable. Okay. Now, fluorine, on the other hand, this fluorine is a stronger base because, one, it's more electronegative. So, it's more electronegative, meaning that it likes to attract electrons to itself. So, it wants to form a chemical bond because the charge is small and localized. Okay? Small, comma, localized charge. And if you compare that to chlorine, chlorine's charge is spread out, so it's less concentrated. But if it's small and localized meaning it's just fixed, or it's in one place. Smaller charge meaning you have much more capability to react and form a bond. Okay? So I like to say here, this will all point to being more reactive. Okay? More reactive. All right, so just a little explanation. If you need a little background there, I'd like to explain that a little bit. All right, so that's our, so now let's just write the reaction in the direction it goes. Okay, so sodium chloride plus HF will proceed in this direction. All right, so shortcut here, just look at which side the weak acid is on. It's going to go towards the weak acid, okay? So here, weak acid, strong acid, okay? So you don't really need to know, for right now, you're just going to compare based off what you know is a strong acid and everything else is weak, okay? So what this tells us is that this reaction, the reaction in the forward direction, does not occur. So sodium chloride plus HF, we write this as no R, okay? So this stands for no reaction. Nothing happens. Okay? So you put these two in there, nothing will happen. Okay? But if you put sodium fluoride and HCl together, you'll get sodium chloride and hydrofluoric acid. All right. Are any questions about predicting the direction here? Yeah, Captain.
Does it apply the same way with bases? It always goes to weak base?
Yes, exactly. Right. Very good. Okay. Any other questions? All right. So now we're going to talk about the trends. How can you tell something's more acidic without looking at a pKa chart, a Ka chart? We'll be able to do that. Okay. So. All right. Determine relative acidity all right. So we may not have thought about this in a while, but how do you determine if something's more acidic than another compound? You're going to look at a few things. One is electronegativity. So electronegativity of A. All right, so this is a conjugate base. So I'm going to abbreviate this as this. All right, so let's say here I have my acid. So let's just compare carbon, nitrogen, oxygen, and fluorine. How do those hydrogen acids relate? Okay, so I have methane, HCH3. Okay, so HCH3, well, we don't really think methane as an acid, right? So that's the weakest. It's less acidic than ammonia. So I'm drawing out this bond because that's the bond that's going to be lost. That tells you that's the H plus being lost, okay? And then water can act as a very weak acid, so HOH. And then HF is the last one, okay? So on this scale, all right, pray that I draw a straight line. All right, so in this direction, we're going to have here, okay, let me move a few things here. All right, thank you. All right, so in this direction, we have increasing. So in this direction, what is increasing from left to right? What property have we pretty much talked about like this whole class? Electronegativity, right. Increasing electronegativity. So I'm going to write this as EN, okay? Electronegativity of the conjugate base. All right. So, but what do we know about these relative acid strengths? Is water a stronger acid than HF? No. So HF here is the strongest. Ammonia is a base. Methane is neither a base nor an acid. So this is where also, let me just draw a different color. This is where we're going to write acidity here increases. So as this, the acidity oh, brother. Increases. Okay? And the reason why this is when you have the conjugate base, right? The conjugate base will be more stable if the atom can stabilize the charge better. And we said things that are more electronegative, they like electrons, right? So they're more able to stabilize the charge. So here on this side, A minus is more stable. Because A minus is more stable, it's a weaker base. The acid is therefore stronger. Okay. Anyone have any questions about that? That trend, electronegativity. Does that make sense? Okay. All right. There's also a hybridization trend here. So, hybridization. Okay. So, a compound can also be an acid. And there's a trend whether or not your atom that bears the hydrogen, whether it's sp3, sp2, or sp. Okay? So, let's draw our atoms here. CH3, CH3. All right, so let's just highlight one of these atoms here just to illustrate what I'm talking about. So, what's the hybridization on this carbon? Oh, any one of them. Because they're both the same, right? They both have 4 bonds. So what's the hybridization on one of these carbon atoms? sp3, thank you. And do you guys remember which hybridization has the highest S character? All right, what's this hybridization on one of these carbons? Yes, sp2. So 2 hydrogens and a double bond, right? sp2. And then lastly, how about this alkyne? So alkyne is this triple bond here with carbon and hydrogen. What's the hybridization on one of these carbons? sp. Good. All right. So in what direction does the percent S character go up? Is it left to right? Sorry, left to right or right to left? Yes. Good. Because remember, if I have 1 S and 3 P, I have 25% S character. And if I have sp2, now I have 33.33 repeating percent. And if it's an sp, what's the percentage there? 50, correct. All right. So in this direction, we have increasing S character. Of my conjugate base. All right. So, if an orbital has more S character, why would you think that will affect acidity? Let's think about it. A conjugate base usually has a negative charge or excess electrons. So, if an orbital is more S-shaped, that means I'm in an orbital that's closer to where? The nucleus, okay? So if you're more spherical in shape, S, you're going to have there's a higher chance you're going to pop up near the nucleus. That's going to stabilize those electrons through the opposite attraction force, right? Okay, so that's why this will increase, the acidity will increase this way. Like that, okay? So let me just clarify why that is, okay? More S character, okay? Negative charge, or in this case, you know, the electrons, right? Is closer. Nucleus. Are there any questions about that? Because guys, what shape is the nucleus? Does it look like a p orbital? No. It's like an enclosed sphere, right? So if you can recall how these orbitals look like, things that are spherical in shape, they are typically more closer to the nucleus than, say, p orbitals and d orbitals. And that has to do with how the orbital looks like, which is described by the wave function. Okay? But just think like this. If you have an spherical shape, you're going to have better overlap with something that's spherical, right? So you're going to there's going to be a probability, higher chance that you can get close to the nucleus. So that's how I see it. Are there any questions about that one? No? Okay. So that was all of A. So electronegativity, okay? The electronegativity of an atom will stabilize the negative charge. And in terms of hybridization, if something is sp hybridized, it will be the most acidic out of all the, these are called hydrocarbons, only hydrogen and carbon, okay? All right. So let's talk about a few more here. All right, so that's A, that's electronegativity. Now let's go to B. All right, polarizability. So this is the size of the conjugate base. All right. So let's look at a series of acids here. So we have our acid column. All right. H, F, HCl, HBr, HI. All right. So from what we know about our strong, so out of all these acids, which one is the only weak one? HF. All right. HF is the only weak one. Okay. The rest are considered strong, but the ones you probably only seen or worked with in the lab is HCl. Okay. HBr and HI, they're more expensive, so we typically don't buy those. They're for very specific purposes outside of the academic lab. Okay, so our trend here is that as we go down this way, you're going to see, how should I write this? I'll write like this. All right, but this trend, it's kind of at odds with the trend we just talked about, right? Because compared to F, what's iodine's electronegativity? Is it high or is it low? Yeah, relatively low, right? That doesn't make sense. How does I have a higher, stronger acid, right? So these trends confuse students a lot because they oppose each other. The first one, electronegativity, HF is the strongest acid, but when you compare it down the column, now the size matter, the relative size of the atom, okay? Because which one of these acids, which conjugate base is the largest? F, Cl, bromine, or iodine? Iodine. It has a humongous shape, okay? And it comes to that thing I talked about. If you have a bigger size, the conjugate base, the electrons in the conjugate base are more stabilized, so it becomes a stronger acid. Okay? So in this case, we also then have increasing. So here we're going to say increasing polarizability. Okay, that's just another name for the general size of the anion is increasing. Okay, so here the conjugate base okay, F minus. All right, then we have Cl. Br. And then I minus. No. Stop it. All right. Okay, so the larger the anion, the stronger the original acid was. Okay, so that's polarizability. So size also plays a role. Okay, all right. Are there any questions about that trend there? Might seem a little fishy because of what we just talked about. All right. Okay, so now. Let's spend some time and talk about resonance. How does resonance plays a role? So that's why I spent a lot of time about resonance because resonance is never going away. It explains a lot of things in terms of what we'll see in this class, okay? So, let's go to letter C, the third trend here, resonance. All right. So resonance, I don't know if you've heard this phrase before, but there's a phrase called resonance stabilization of the conjugate base. Okay, so if resonance can move the charge around, that is another way of stabilizing and making an acid stronger. So stabilizing a charge, all right? So I like to put it this way, stabilizes. But by moving,
Professor Andrew?
yeah,
Sorry, we're going back up to B. Are you talking about the conjugate bases as you go down, it's increasing stability?
yes,
Okay, and
that's
then
what I mean.
the acidity increases on the left side for the acid?
Yes. So the acid, right. So the arrow there is for those acids. I'm referring to those acids. And then the size of the conjugate base is on the right. Yes. Any other questions on that? Anything confusing? No? All right. So resonance stabilizes the charge by moving it around. Okay. So let's look at two examples. One, we have ethanol, so CH2, sorry, CH3, not CH2. All right. Oh, sorry guys. Erase this H for a sec. I need to draw the bond. Okay. So if I put this in water, okay, so I'm going to write water backwards just to illustrate this bond being removed and going back to the oxygen here. All right. So let's write the conjugate base. Man, I should have wrote the bonds out. It's okay. All right. So there's a term called pKa. I'll refer back to a lot. You don't have to memorize any pKa's, but it might be helpful if you do, just because of all the functional groups we'll talk about. Okay, but I'll come back to that later. So alcohols in general have pKa's around this value. So pKa is 16. All right. So the pKa I'm referring to is this hydrogen. So each different hydrogen here will have a different pKa value, but you'll always remove the hydrogen with the smallest pKa, because remember, like pH, lower pH means what? Your solution is more acidic. So if we're trying to detect which compound's more acidic, pKa is the measure of how acidic a compound is. Okay? So here, I will say here, let's just revisit what a pKa is. All right? Measure of how strong an acid is. All right. I don't know, my iPad's dying because it's lagging like crazy. So I'm going to have to stop soon. Okay? So remember, pKa's are on, they're not they're not directly comparable, right? A pKa of 16 versus a pKa of 4. You might think that's a change of just four times, but pKa is based on a log scale, so you can't consider that. Okay, it's more like 10 to the fourth power difference. Okay, so something could be 10 to the fourth power more acidic just by a few pKa units. Okay, so just like pH, the smaller the pKa, the more acidic something is. Okay. All right, so that's an alcohol. Now let's compare with a carboxylic acid. All right, so let's use the second example here. H3C. Okay. Does anyone remember the pKa of acetic acid? And sorry if you don't. Because you guys did so many titrations before, so might all been a blur. All right. So say your acetic acid dissolves in water and it releases hydronium ion. Okay. All right. All right. So the pKa of acetic acid is 4.76. All right. Well, what gives? That's such a high difference. And the hydrogen is still attached to the same electronegative oxygen atom, right? So what's the big deal? Why is it so different? Okay. And the reason has to do with how that negative charge over here on the right side, how it's shared between other atoms in the molecule. Okay. So I'll tell you right now that this is the way stronger acid. Okay. So stronger acid. All right. And it's approximately 2 times 10 to the 11th power times stronger. Okay. If you're curious how I got that number, I took the pKa's and I converted them back to their regular number. So I did the antilog of the pKa values, and then I divided them, found the ratio between them, and it's this huge number. Okay, so a difference of about 12 units approximately is a 10 to the 11th power fold increase in acidity. So it's very, very different. Okay, so now let's explain why does resonance play a role here. So if you consider the resonance structure, so can we draw a resonance structure here? H3C. Oh wait, sorry, don't draw that. All right, let's keep it there. Sorry, guys. Okay, so let's draw a resonance structure. So how am I going to draw this new resonance structure? Any guesses? So let me just move the arrows if that helps you. So one thing I could do, right, is I could switch where the double bond is and the charge. So I'm just drawing these arrows to illustrate, okay? So I'm going to draw the negative charge here. like that. Okay? So, because the negative charge is shared between both of those oxygen atoms, it's more stable. And this is called resonance stabilization. Okay. Of the conjugate base. All right. So this acid is way more acidic is because compared to number one, this charge is shared between two electronegative atoms. That's particularly stable. But is this charge shared in number one? No, right? It's only being supported by one oxygen atom. So that's the difference. In number one, the negative charge is solely on the lone oxygen atom. In number two, you have two resonance structure that delocalizes or spreads the charge over between two atoms. Okay? And that's usually the key. If something has resonance, that will influence its acidity, even more so than just having an electronegative atom holding the charge. All right, so let's take a little break and we'll get back. Take about 7 minutes. Take the quiz.